Hi, welcome back to our lecture, Practical Guide to Quantitative Finance Interviews. So today we will continue talking about dynamic programming. So dynamic programming basically refers to a collection of general methods developed to solve sequential or multi-stage decision problems. So it is an extremely versatile tool with application in fields such as finance, supply chain management, and airline scheduling. So although theoretically simple, mastering dynamic programming algorithms actually requires extensive mathematical prerequisites and rigorous logic. So as a result, it is often perceived to be one of the most difficult graduate level knowledges. But again, so the dynamic programming problems that you are most likely to encounter in interviews are quite simple. They just have the basic fundamental ideas of dynamic programming, but does not require you to do anything related with algorithm to combine them into a quite complex project. Okay, so here I'm going to introduce several examples which are going to cover the gist and power of this method. So all the dynamic programming talked about here will be discrete time dynamic system. Of course, we have continuous time, but that's quite advanced, and we cannot do that during interview question level. Okay, so a dynamic programming problem can always be divided into stages with the decision required at each stage. So each stage is going to have a number of states associated with that. And the decision at one stage is going to transform the current stage to the next one. For example, if I currently have $1 and I earn $1, I'm going to change my stage from owning $1 to $2, okay? And assume that the problem has, let's say, n+1 stage, which is basically just also time period. And following the convention, we are going to label them as just a 0, 1, all the way to n, okay? So we're starting from 0, which is the initial stage. And the state transition can be expressed as something like x at some point k+1 is going to be a function of xk, which is the previous stage, and the uk, which is our method, utility function, and also wk. So this uk is the decision. I'm going to write it here. And wk is the random parameter, which we also call disturbance. Okay, so this is the basic setting, but then according to different policies, according to different actions that you are going to make, you actually can have different kinds of results, different kind of final cumulated state value. So a set of all the decisions is going to be our policy, which can be write as pi. We usually call it pi. And it is going to be set from mu0 all the way to mu n, okay? If we have n here, then it is n-1, because at the last stage, we do not need to change anything. And the goal for a system like that is basically to minimize the cost function or to maximize a profit function. If it is a cost function, then it is minimized, okay? So we can call this function as gn xn, and this should only depend on xn, okay? So has no relation with all the previous states. So it's a little bit like Markov chain. And our target is just to minimize this function, which is going to be, let's just use the case with cost, okay? Minimize the expectation of gnxn plus from k equal to 0 to n-1, gk, and xk, mu k, wk, okay? And we know that all the set of mu k is the only thing that we can change by ourselves subjectively, and it is the policy. So basically, we are trying to find the best policy, which is going to help us to minimize our cost or to maximize our profit. And by this, we can know that the dynamic programming algorithm. So basically, the dynamic programming algorithm relies on an idea called the principle of optimality. And if we have already found our best policy set for the original dynamic problem, then the tail policy with a random place of all these things must be optimal for any sub-problems, which means, for example, if we from state 0 to n, we already have the best one, then this policy should also be the best if we only start from, let's say, state n divided by 2 and all the way to n. So if we only take half of this process, it's still the best because it is going to be the overwhelmingly best situation, but not local maximum or minimum, okay? So to solve this one, the classic method for a static system is going to be think backwards. I believe this kind of method we have applied times after times during our previous lectures. Sometimes we started from the last one and go all the way backwards to our initial stage, right? And basically it is where it comes from. So, and by this, we usually generated the expected optimal cost. But one of the things is that it only means that we can already find our eventual goals and the eventual returns. If we are at a point where the future we does not know, then we cannot use this for backward stage, right? Because if we are still at the initial point and this is just the precedent, then we cannot go back because we are already at the 0 time, but not the n time. So let's start by some examples. The first one is, again, dice games. I think we already have rounds dice games. So you can run a 6-side dice up to 3 times. And after the first or the second roll, if you get a number X, you can decide either to get X dollars or to choose to continue rolling. But once you decide to continue, you are going to forego the number you just rolled, okay? And if you go to the third row, you are going to just get X dollars if the third number is X and the game stops. What's the game worth and what is the strategy? So basically the key part is that what is my strategy? So again, we combine 2 methodology together. One is think backwards and the other one is we started from the simplest case. So our simplest case is that we can only roll up to 1 times, okay? In that case, then there is no strategy, right? We just toss it. And the expected return of this incident is going to be what? 7/2, right? But how about if we have 2 times? Then after we have already rolled our first dice, we need to decide whether we should forego the number or we should keep it. And of course, this value, this threshold to keep should be larger than 7/2, right? Why it is the case? Because we are only going to keep this number because we think it is already large enough. For example, if we already tossed a 6, then of course we are going to keep that. But how about 5 or how about 4, right? So the threshold should be larger than 7/2, and 7/2 is just 3.5. So basically, if there are only 2 times for us to roll, then we are going to keep 4, 5, 6 for the first time, and then we toss the second time. And for this situation, the expected value is what? We have 1/2 probability to get either a 4 or 5 or 6, and the expected return is just 5. And we have another 1/2 probability to get 1 to 3, where we're going to toss it again. And it is going to be multiplied by expected S, right? Because for the second time, we are going to accept any number it reveals. So in total, this is going to give us 7/4 here, and this is 10/4. So basically we have 17/4, which is just 4.25, right? And then now we know the 3 times. So if we can roll up to 3 times, then for the first time, we will only keep 5 or 6, right? And the probability of that is 1/3 to have 2/11. And there are 2/3 probability to have this ES2. Okay, let's call it ES1. So ES2, and this should be ES3. And this is going to be 14/3. So this is our expected game odds, and the best strategy is basically we should keep 5 or 6 during the first round and keep 4, 5, 6 for the second round. And otherwise, we are just going to forgo the number and continue to the next round. Okay. So now let's come to the next question, which is what series? By the way, starting from this question, we need to solve the correct answer by computer, by Excel, by Python. So we are basically trying to just list out the formula and to let you understand how to solve this question. And basically, that's what also the interviewers expected for any dynamic program question, unless they are asking you to code, right, to write some codes on their platforms. So for here, if it is a written question, then basically you just need to explain what's your strategy and what's the formula and how can you solve each step's result, okay? So for this question, we have the Boston Red Sox and the Colorado Rockies, and they are playing in the World Series finals. In case you are not familiar, there is a maximum of 7 games. So basically, 7局4胜. The first team that wins the 4 game claims the championship, and you are going to have $100 to place a double or nothing bet on the Red Sox. But unfortunately, you can only bet on each individual game, not the series as a whole. So we already know that if Red Sox win, I'm going to win exactly $100. But if Red Sox loses, which means the Colorado Rockies win, I'm going to also lose exactly 100. So let's define IJ, where I is the game won by Red Sox, okay? And J is games won by Colorado Rockies. We know IJ ranged from 0 all the way to 4, right? And we already know that for FI, for all these 4 combinations, 4, 0, 4, 1, 4, 2, 4, 3, we are going to equal to 100, right? And also we have 0, 4, 1, 4, 2, 4, and 3, 4. We are going to have negative 100. And how can we solve out that the other stages, for example, F00 or F01, right? So what's our return? So basically we know that Fi plus 1, let's try to write it here, sorry. So we know that Fi plus 1j is going to equal to 1. It's going to equal to Fij plus our bet. So this is our bet. We call it y, okay? And Fij plus 1 is going to be Fij minus 1, right? And combine these two together, basically we can find there are in total 4 things, and we can know these two, right? These two we can know because we can have 4, 3, and this is 3, 4, we already know that. And now we want to solve 3, 3, for example. And basically if we replace this as x, y, x, y, so we have 2 variables for us to solve, and we have 2 equations, so we can solve this out. And we actually can find Fij is going to be 1/2 multiplied by the sum of Fi plus 1j plus Fij plus 1, right? And on the other hand, y is going to be Fi plus 1j minus the Fij plus 1. And it is going to be divided by 2 as well. And from 4, 3, and 3, 4, we can solve 3, 3, and from 3, 3, and for example, 4, 3 together, we can get what? We can get 2, 3, right? And all the way back, we can solve all the things out. Basically, we know how to solve this question. And now the next one, dynamic dice game. So a casino comes up with a fancy dice game. It allows you to roll a dice as many times you want, unless a 6 appears. Okay, and after each roll, if 1 appears, you will win 1. 2 appears, you win 2. If 5 appears, you win 5. But if 6 appears, all the monies you have won in the game is going to lost, and the game is going to stop. So after each roll, if the dice number is 1 all the way to 5, you can decide whether to keep money or keep on rolling. How much are you willing to pay to play the game if in the case that I'm risk neutral? So basically it is asking the expected value of this game was, right? So assume we already have $N, right? If we already currently have $N, then the return is actually we have 1/6 chance to get N plus 1 if we have 1, N plus 2 if we have 2, and N plus 3 if we have 3, N plus 4, and N plus 5. While we also have a case that's 1/6, we're going to have 0. So this is going to be 5/6n plus 2.5. And we want this value to be larger than our current state, which is n. And we can find n should be smaller than what? Smaller than 15, right? So the maximum value that we are going to win from this game, I'm going to keep is 14. And if we stop at 14, then the maximum payoff of the game is 19. Why it is the case? Because if we currently have $14, then we are going to play, right? So at that time, if we got 6, of course we lose everything. But if we got a 5, then our final result is actually $19. So keep notice of that. And we already know that F19 is going to be 19. This means if we start from 19, start with 19, and our return is basically 19, okay? And F18 is going to be 18 all the way back to F50 is going to be 50. And we know that the expected value of Fn conditional on n is smaller than or equal to 14 is going to be simply 1/6 and sum of expected value of Fn plus I, right? I equal to 1 to 5. Because if we are at the 14th, let's say 13, then it is possible for us to get 14 or 15. And since we already know this 5, we can go all the way backwards to what? To F0. And actually we can, by solving that, we can actually find F0, the expected value of F0 is going to be 6.15. So I'm going to be willing to pay $6.15 to play the game, okay? Now, the second last question, dynamic card game. So again, a casino. This time it offers a card game with the standard 52 cards with 26 red, 26 black. And the cards are thoroughly shuffled and the dealers draws cards one by one. So you can ask the dealer to stop at any time you like. After each round, basically you can stop. So for each red card drawn, you win $1, and for each black card drawn, you lose $1. So what is the optimal stopping room in terms of maximizing expected payoff, and how much are you willing to pay for this game? So I think at this time, you should already find that for all the dynamic programming questions, they are trying to ask you to find certain policy and trying to maximize or minimize something, or to find this threshold that you are willing to do something or not to do something, right? By calculating the expected value. And basically that's the fabric or the pattern for all these kind of questions, okay? So for this card game, if I denote B as the number of black drawn and red as number of red cards drawn, and our return is going to be what? It's just black minus R, right? So if we stop at BR, our return is going to be B minus R. But if we continue, then our return is going to be, we have B over B plus R probability. If we have drawn B and R, then we are going to have B black cards. We are going to have R black cards left and B black cards left, right? So we are going to have B over B plus R probability to have FB minus 1 R, right? Oh, sorry, this should be the black left. Okay, let's denote this with red left, and then it should be B minus R. Otherwise, it should be R minus B, right? Because we are going to get dollars only by red cards. So if there are B black cards left, how could this be possible is that if we have drawn R red cards and the B black cards, our return is R minus B. And this is basically the same as this as the red card, the black card left, and this as the red card left. So we can denote in this way, okay? Because if we have more black card left, then we are going to earn some money, okay? And in this case, we are going to have this formula. Our return is going to be R over B plus R, and this is having B while R minus 1, because our next round we are going to have an R card, right? And by doing that, we already know that F0R is going to be 0, while FB0 is going to be B, right? Oh, sorry, by 0R, we are actually losing R. And if we have 0R left but B black left, this is going to be negative R, right? And by combining these two together, we can find what? We can find the expected value of F26, our initial stage is 2.26. Just by having this formula and compared it with B minus R. So we are trying to find the max of these two, right? And F00 is going to be 0, okay? Because the number is equal. And that's all for this part. But event now, finally, we are going to have one more question, which is an advanced topic in dynamic programming. The question itself is quite simple. It's called color balls. So basically, a box contains n balls of n different colors. And each time you are going to randomly select a pair of balls, repeat the first to match the second, and put the pair back into the box. And what is the expected number of steps until all balls in the box are of the same color? Okay, so in the question, it already said it's very difficult. I'm going to solve this question using two ways. One is from the green book, which is a quite classical way to solve that. But I'm also going to introduce one which I learned from Stack Overflow. You know, Stack Overflow is actually a quite good website. It's basically the Google engine for all the STEM students, okay? And I'm going to also illustrate that solution, which is more simple and more elegant. But let's start with the classic one. Okay. So let's first think about, originally we have n colors. So we are going to denote n as the number of steps needed to make all balls the same color, okay? And we can have this expected ENN have the same color, small n, okay? It is going to be what? The expected value of n of having color F1, okay? Multiply the probability F1 plus all the way to expected NN Fn with the probability Fn. Since all the colors are symmetric, by applying the principle of symmetry, we are going to have all of these probability F1 is going to equal to probability Fi is going to be 1 over n, right? Because they sum together, it is going to be 1. We know that eventually all the balls in the box are of the same color. If we keep keep selecting the pairs and doing this process, so that we can now we can only need to solve out what ENN of F1 multiplied by P F1, right? And all these expected value are also the same. So we already know this is 1 over n. So we can only need to solve this part. So how can we solve this part? This is, of course, a Markov chain and also a martingale. So if we only consider the event F1, color 1 is different from other colors, and the color 2 and 2, 3, all the way to n becomes equivalent, right? As long as it's a different color from color 1. So in other words, any pairs of balls that have no color 1 ball involved are equivalent, and any pairs with the color 1 ball and the ball of another color are equivalent, if the order is the same as well. So we only need to use the number of balls that have color 1 as the states. So our absorbing states is to having n balls, right? Where it has n, and we have some probability to form n minus 1. And let's say our starting state is we are currently have I balls that have in color 1. And it can also reduce to all the way to 2, 1, right? But at least there should be 1, because we are considering the case that we are going to convert it to color 1, okay? There is no state 0, otherwise it is going to never reach F1. We are not going to give that possibility. So now we can find what? We can now listing out expected value of Ni F1 is just equal to, first, originally, we need to plus 1 at the very beginning. Do not forget that, right? It's going to be expected value of Ni minus 1 F1 multiplied by probability I minus 1 conditional on F1 and plus what? Plus expected value of still having Ni F1 of probability I. Do not forget the case where we can still remain in the same state, okay? And we can have Ni plus 1 F1 probability I plus 1 F1, okay? So we can have all these 3 parts, and now we just need to solve all this probability. So for this probability, it could be rewritten as what? As probability xk plus 1 is going to be I minus 1, while the case state is I and conditional on F1, right? And now we can use the Bayesian. It is going to be equal to what? Probability sk equal to I f1, and probability xk equal to I x k plus 1 equal to I minus 1 and f1. And this is going to be, we can see we both have f1 here, so it can be canceled out. Why it is the case? Because we can write both it into probability f1 conditional xk equal to I multiplied by probability xk equal to I, right? Sorry, we are not going to cancel out these two. We are going to cancel out these two because we are trying to get the f. And on the numerator, we can have probability f1 conditional on both xk minus k plus 1 and xk, right? Multiplied by probability sk plus 1 equal to I minus 1 conditional on xk equal to I, and multiplied by conditional probability, the probability of xk equal to I. So these two cancels out. And how about this part? Conditional, we currently have I balls. What's the probability of f1 habit? Basically, when n balls go to the color 1, it should be I over n. Why is the case? Because originally, when all n balls have different colors, each of it has a probability, fi has a probability of 1 over n. But now, within these n balls, I of the balls have already been all color 1. So we can think it as a whole group. And each of them brings us 1 over n probability. So in total, there are I over n probability, okay? And how about this part? Probability f1 conditional on this thing. So for this part, it should be I minus 1 over n, right? Because after we have, after xk plus 1 is going to be I minus 1, there should only be I minus 1 color 1 balls in the system. And now it is the only part left. This part is that we need to pick out I balls from n, which is color 1. And meanwhile, we need to pick out what? N minus I, any other color balls out in the system, and with n minus 1 probability, right? So combining all these three together, what can we find? We can find this whole thing is going to be equal to I n minus I, and this is n minus 1. Okay? Because let's put it together. I minus 1 over n, and this is n minus 1, I n minus I. So this I cancel out, this n cancel out. So we have this left. Okay. Oh, sorry. This is should be I minus 1. And similarly, we can find probability. This is xk plus 1 equal to I minus 1, right? Similarly, we can find xk plus 1 equal to I plus 1. Okay, not minus 1. Conditional xk equal to I f1 is going to be just a guess. The denominator should be the same, right? N minus 1. And how about the numerator? The numerator is going to be still n minus I, but this time it is going to be 2. This is going to be I plus 1. And the probability that xk remains the stage, f1, is going to be n minus 1. Again, guess. So still the same, n minus I. So this part, it should be I. Do not forget to multiply a 2. Why it is the case? Because if we state at the same situation, the sequence of the first ball we pick and the second ball we pick does not matter, right? There are 2 cases in total. But in any other two cases, when sk plus 1 equal to either I plus 1 or I minus 1, we need to ensure the first ball is the color that the first ball is going to be the color 1, or either the second ball is going to be the color 1. Because in the question, it already ensures that we are going to only use the first one to match the second, but not the second to match the first, okay? But it doesn't matter in the same color situation. And we replace this 2, 3, and 1 back to this part. We have this, we have this, we have this, and then we can using some boundary case to calculate all the values out, okay? And this is actually going to give us that this expected we can actually have this thing is going to be n minus 1 square 2. Okay. And then in total, how many have we have? We have 1 over n, right? So it should be n over n plus n minus 1 squared. Okay. So this is the classic solution. I think it is a quite long thinking process, and it's actually quite hard for you to think of that during an interview. But is there another way to solve this question? Yes, there is, and this is actually quite elegant. So let's think it. At the very beginning, we have n balls with n colors, right? So for our first pick, since there are n colors for n balls, each one it is a one-on-one map. So this is the original stage. At our certain state, we are still going to have n balls, but we have 100% to have only n minus 1 colors. Why? Because for each color, there is only 1 ball left. Right, at the initial stage. Now let's jump all the way back to the last stage. Okay. So we are going to have n balls, and we are going to have 1 color. So our second lot is going to be what? We have n balls, while we have n minus 1 for 1 color, and 1 for the other color, right? And can you find something interesting? That is the only thing we need to care here. The only steps among all these steps from here, the only steps we need to care is the steps that there are going to be only 1 ball for a certain color. And it has been picked, right? We only need to care about this stage. And how can we do that? Then we only need to consider the number of colors left in the system. So to consider this, it is just a geometric distribution. Well, the probability is that among n balls and n minus 1 balls, we are going to pick at certain steps, there are k colors, and we are going to pick k minus 1. So k is just number of colors left in the system. So we are going to pick any of the colors at the very beginning, and we pick the other one. And we are thinking it as a geometric distribution. What is geometric distribution? It means after a lot of times of failure, the first time you get win, right? The first time. So in here, it is just the equivalent to what? The first time, one of the color still in the system has only one ball and it has been picked up. So this is just the probability P for this geometric distribution. So it follows P and P equals to this. So the expected steps is just what? 1 over P according to the property of geometric distribution, which is just K, K minus 1, and N minus 1, right? And we just need to take the sum from K equal to 2 all the way to N. Remember, this is not K equal to 1, because if there are only one color left, we can never find a pair which could reduce this, reduce the number of colors in the system, right? So this is just N minus 1, K minus 1. And we take N minus 1 out. The system becomes what? 1 over 2 plus 3 multiplied by 2 plus 4 multiplied by 3. And we all know this is what? This is 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 all the way to minus 1 over n. So basically it is n minus 1. And this n is cancelled out. So we have n minus 1 squared, right? And since we can reduce to any kind of a color, so it should be what? N over n minus 1 squared. And this is the expected value. Okay? So this is, I think, is a more elegant way to solve this question. It is going to be super impressive if you can use this kind of logic. And so in this method, we are actually using one of the ideology we talked about before. That is, we think about the tail. We think about the last one that is going to change the system. Because in a lot of situations, only the last one matters. Okay, only the last one or the first one matters, but in most cases, it's the last one. And I hope you enjoyed this question, and feel free to review it on Green Book. And so 不要忘了一键三连. Let's see you in next lecture, where we are going to talk about Brownian motion, which is just the preface and the pre-lecture for our financial derivatives part. And we're going to talk about Black-Scholes models shortly. Okay, thank you for watching.